All right, let's go through our practice exam, chapters 15 through 18 for exam 2. So first up, will this reaction occur spontaneously at standard state conditions? And I have a chemical reaction here, so I have no other information. So the one thing I do have at the end of the exam is all of the standard reduction potentials. So that's probably what I'm going to need to use. So I'm looking for gold and gold 3+. And hopefully I can find that somewhere. All right, so gold is 1.5. And then potassium and potassium plus is negative 2.92 volts. So since gold is higher on the list, the spontaneous way would be if gold is the cathode and potassium is the anode. So the cathode is the reduction and the anode is the oxidation. So let's see if in this equation that's what's happening. So here I have gold going from 0 to 3+. That is going up in charge, so that is not being reduced. So this is not going to be spontaneous. All right, next up for the reaction, I have a delta H and I have a delta S. Which of these statements are true? The reaction is spontaneous only at higher temperatures. At 25 degrees Celsius, it's equilibrium, only at low temperatures, spontaneous at all temperatures. All right, so we need to think about this. When I have a delta H that's negative, that's exothermic. That means energy is given off. And when I have a delta S that is positive, that is an increase in entropy, an increase in randomness, which is more likely to be spontaneous. So this is more likely to be spontaneous, and this is more likely to be spontaneous. So this will be spontaneous at all temperatures. You can also think about the equation. Right, so if this part's negative and this is positive, so this whole thing is negative, it's always going to add up to a negative number. So whichever way you want to think about it. All right, a negative sign for delta G indicates, well, we talked about that a little bit. I sort of alluded to it. So if this is negative and this is negative, delta G will be negative, and negative means spontaneous. And I didn't even have to read the other choices because that's what it means, right? There's nothing else that it doesn't mean anything about endothermic or exothermic. It doesn't mean anything about speed. It doesn't mean anything about delta S. All right, which one of the following is capable of transforming Cu2+ to Cu solid? Okay, so this is talking about this reaction, which is a reduction. Right? So I'm looking for something that could oxidize it. So first of all, what I'm going to do is find copper on my list here. And it's the copper, not this one down here, down here, which is copper 1+ to copper 0. I want this one here, which is copper 2+ to copper 0. So I want this to be my reduction. So I'm looking for something under it to be my oxidizer. So then let's see if we can find some of these things. Aluminum is good, that's under it. Iodine is higher. I- is right here, so no. Nickel is under it. Fluorine is the top of the list, so no. Silver is here. So how do I decide between aluminum and nickel? Well, then I need to think about what's the actual reaction that would be happening, right? So if this is a reduction, then I need the oxidation. So I need nickel becoming nickel 2+, or aluminum becoming aluminum 3+. So aluminum 3+ wouldn't be the reactant, it would be the product. Nickel neutral would be the reactant. All right, which of these has the highest entropy? I'm going to look for a gas first, and since I only see one gas, that's it. 6, this one seems extremely familiar because apparently I put the same question on here twice, so we'll just move along. Which one of the following combinations cannot function as a buffer? So one thing I'm looking for is that they have the same anion, but they all do. And then the other thing would be like that another thing would be that the hydrogen's replaced with the metal, which is that's true as well. So the only other thing I can look for is it has to be a weak acid or base. So are these weak acids or are any of them a strong acid? HF is weak, HCN is weak, HNO2 is weak, but HNO3 is a strong acid. If you have a strong acid, you don't have equilibrium, and then you don't have a buffer. All right, which of the following would decrease the solubility for PbI2? So it's got these options here. Let's think about what they're asking me about. They're talking about lead iodide separating into lead and iodine ions. Would heating the solution make a difference? Probably. Usually for solids, for solubility, heating the solution makes things more soluble, but I really need a delta H to know for sure. Lowering the pH, that sounds unlikely to really make much of a difference here. Maybe I need to think about if it's an acidic or basic salt, but that seems complicated. But what about this one? Adding a solution of, here's a common ion, that would decrease the solubility, absolutely. So I'll just give up on the pH idea. Okay, find the EMF of a cell. Okay, so this is a cell diagram, which is anode on the left and cathode on the right. And so then I just need to find those numbers, and then my E cell equation is cathode minus anode. All right, so for the gold, found that earlier. Can I find it again? How much of this video is going to be you guys seeing where it is, me like, you're looking right past it? All right, here we go. 1.5. And then the iron and iron 2 plus. I see iron 3 plus here. Iron 3 plus. Here it is. Iron 2 plus. So negative 0.44. So when I add that together, so this negative and negative, so it should be 1.94. All right, and then finally, which is the best choice for preparing a buffer with pH of 3.5? I want to look for the pKa's of all of these because the pKa's are the buffers work best near their pKa, plus or minus 1 pH point from their pKa. So I'm going to do minus the log of all of these. I get 5.4. So, I mean, that's a little bit out of the range, right? So probably not great. Three. 8.6. 3.5. And 4.754. So I was ready to say that B would be good because it is 3, but this is even closer, so the closer the better. All right. Complete and balance our redox reaction. So the way that I'm going to do that is separate my elements into half reactions. So I'll put lead in one, and chlorine in the other. Cancel any, balance any elements that are not oxygen or hydrogen, so 2 chlorines. Balance oxygen with water. There is no oxygen in the bottom half reaction, so I just need two H2Os up here. Balance hydrogen with hydrogen ions, H plus ions. There's no hydrogen in the bottom one, so I just need 4 H pluses over here. And then balance my charge with electrons. In the top one, I have 4 plus and 2 plus. So I'll make it 2 plus and 2 plus. And in the bottom one, I have 2 minus and 0. So I need 2 minus over here. If the electrons don't cancel, make them cancel, but in this case they already do, so I have 2 and 2, so I cancel my electrons and add them up. And actually I'm looking at the equation sheet. This is the answer on the equation sheet, but this is the answer in acidic. This is not actually the answer in basic solution, so I'm going to have to fix that. All right, so for basic solution, I want to get rid of all my H pluses. I do that by adding OH minuses, 1 per H plus. Because this is already balanced, I need to do it to both sides. I probably should have checked if it was balanced, but I'm going to just do that at the end. Okay, so this is 4 H2Os now. And that cancels with these 2 H2Os. Well, 2 of them cancel to make 2 H2Os on the left. So now I have 2 H2Os, PbO2, 2 Cl minus, Pb2 plus, Cl2, and 4 OH minus. I know this is basic because it has OH minuses. That's the excess ion that it has. All right, let's check our elements. I've got 4 hydrogens, 1, 2, 3 oxygens. No, 2, 3, 4 oxygens, 4 oxygens. 1 lead, 2 chlorine, 2 chlorine. Total on the left is minus 2, so 0, 0, and minus 2. Total on the right is 0, plus 2, and minus 4, which is minus 2. So all my elements are balanced and my charges are balanced. So this is my actual answer. All right, here I have all of my thermodynamic data that I need to calculate all these various things. So I'm going to just kind of go through this and you'll be able to see what I did, but I'm going to do products minus reactants for each one of these. You can see all the stoichiometric coefficients are 1, so it's just going to be the numbers from the table, and I'm just going to have to find them carefully. All right, when I'm putting these in my calculator, I like to just distribute stuff, so I'll show you what I mean. So this is negative 393.5. No, negative 390, oh my gosh, 5.2, there we go, plus 90.4. And then this is minus a negative, so I'm going to do plus 296.1, and then this is minus 33.85. For a total of negative 42.55, and that would be kilojoules per mole. 256.2 plus 210.6 minus 248.5 minus 240.46. Negative 22.16, and that would be joules per mole Kelvin. And then finally, negative 370.4. You do have options for how you would do this one, right? You could do the delta H minus T delta S. We'll do that in just a second, but I just wanted to make sure you know. And then minus a negative, so plus 300.4, and then minus 51.8. All right, on my equation sheet, I can get the equation that relates delta G and K, so I'm going to use that. I need to get K by itself. I'm going to just do that ahead of time. So I'm going to divide by negative RT. So natural log of K equals delta G over RT, and there's a negative sign. And then to get the K by itself, I need the exponential. So it's K equals E to the, all right, so now negative 35.1 or positive 35.1 kilojoules per mole divided by R, which is, remember I want the one with joules in it, but I want, if I left this in kilojoules, I have to convert this. So 0.008314 kilojoules per mole Kelvin, and then 298 Kelvin. Okay, I'm going to do my exponent ahead of time. So 35.1 divided by 0.008314 divided by 298. And then I'm going to do the exponential of that. And I get a giant number, so I'll put it in scientific notation. 1.42 times 10 to the 6th is my K. It should be big, right? This is very spontaneous, so it favors products. All right, and then finally delta G. At a different temperature, I need to use delta H minus T delta S. I have all of the numbers that I'm going to need for that up here. I just need to be careful with my units. So my delta H is negative 42.55 kilojoules per mole. My T is 398 Kelvin. And my S is the negative 22.16. But remember, if this is in kilojoules, it needs to also be in kilojoules. And I get negative, uh-oh. That's not what the answer key said. Oh, whoops, I put an extra 0. Hold on. There we go, that's what the answer key said. Negative 33.7 kilojoules per mole. All right. Moving on. At what temperature will a process be spontaneous when delta H equals this and delta S equals this? So I need that same equation. Remember, when we're talking switching spontaneity, we're talking about not really spontaneous or not really not spontaneous, right in between. So delta G equals 0. And we have negative 19.1 for our delta H, minus T is our unknown, and then delta S. Again, I want to match up those units, so I'll put 0.060 kilojoules per mole Kelvin. Or you could solve this ahead of time. I kind of prefer that sometimes, but whatever, it doesn't matter. I need to get T by itself. So first I'm going to move this to the other side by adding it. So now it's plus. And then this is 0.06 times T, negative times a negative, so this is also positive. And then I just need to divide. And I will get the kilojoules and the moles will cancel out. Kelvin in the denominator of the denominator. And so that will be a temperature in Kelvin at 19.1 divided by 0.06, 318 Kelvin. Remember, if you got a negative answer for that, then that would mean it never switches spontaneity. It's either always spontaneous or never spontaneous. But in this case, because the delta H and the delta S have the same sign, there is a temperature where it switches, and it's 318 Kelvin. Also, what if it asked if it was above, if it's spontaneous above 318 or below? Think about that. For me, honestly, the easiest thing I would do is just go back here and plug in a number above or below and see. If I didn't want to do too much thinking, then the math will just tell me. So maybe I'll pick 300 minus 300 times negative 0.06, and I get a negative answer. So it's below. We did talk about how to figure that out. Remember, if we want it to be negative, we want this part, which is going to be negative, to win. This part, the negative and the negative cancel and become positive. So we want this part to be small. So we need a low temperature. So it would be below 318, but I could do it either way at this point. All right, a buffer problem. All right, I've got my acid here because it has the extra hydrogen, and then this must be my base. I'm going to want to figure out my pKa because I'm going to need that a bunch of times throughout this problem. So I like to just do that up front, minus the log of 1.8 times 10 to the minus 5. And I got 4.74. The Henderson-Hasselbalch equation is on your equation sheet. Remember, it is the pKa plus log of base over acid. The pKa is 4.74 plus log of the base 0.275 over acid 0.20. And I got 4.88. Then what happens if I add HCl? Remember, this is a strong acid and it will separate. All I care about is the hydrogen. It will combine out of my buffer here. It will combine with the anion to make whole acid. All right, in my little ice table where we're not in equilibrium, we're going to the end, but we'll still set it up the same way. We've got 0.01, 0.275, 0.2, and get rid of all the strong. So minus on this side and plus on this side. Once I've got those new numbers, I go back to my Henderson-Hasselbalch equation, and I got 4.74 pH equals pKa, there we go, plus log of, now it's 0.265 on top and 0.21 on the bottom. If I'm adding an acid, my pH should go down, not by a lot, but by a little bit. So let's see if that's what happens. 4.84. Check. All right, and then finally, what will be the pH after? All right, so now I'm adding OH. I'm adding a base. Again, there is sodium. It will separate, but I only care about the OH. Remember, the base will combine out of my buffer original components. It will combine with the whole acid. It will grab one of the hydrogens and leave behind the A-. Remember, we're not making anything new on the product side of our buffers. We're just doing some Le Chatelier's principle, shifting around stuff. All right, so I've got 0.04. It says the original buffer, so I'll go back here to 0.2 and 0.265 and get rid of the strong stuff. We don't care about water. So this one, I better use my calculator and make sure I'm not making a mistake. There is 0.16 and 0.305. So now it's 0.305 on top and 0.16 on the bottom. This time the pH again shouldn't change by much, but it should go up a little bit because I added a base. And it did. All right, getting there. Nearing the end here. All right, we've got an electrolysis problem. I've got amps and I've got minutes. Remember, if you have grams, you start from just grams, but if you have Amps and time, you start from amps times time, but you really want amps times seconds. So let's convert to seconds. Now I have amps times seconds. Then I use Faraday's constant, 96,500 amps times seconds per 1 mole of electron. Then I need to go from moles of electrons to moles of whatever I'm trying to get here, which is cadmium. I'm looking for cadmium metal. I can see here it must be cadmium 2 plus. So this is 0, that's the metal. This is 2 plus. So I need 2 electrons to convert 1 mole of cadmium, or 2 moles of electrons. So 2 moles of electrons per 1 mole of cadmium. And then I just need my periodic table to look up the molar mass because it asks me for the mass in grams. Cadmium is 112.4 grams per mole. So I'm just doing some unit conversions. Don't forget that you always need to use Faraday's constant, and don't forget to write your half reaction so you're really thinking about how many moles of electrons and how many moles of stuff. So, but I did those parts, so now I'm ready to put in my calculator. 1.76, 256, 60. Can't really see what I got, but 15.7 grams. All right. Next, I've got an a galvanic cell question. So I've got copper, which is being, well, let's start with which one's being reduced, which is the silver, because it's going down, right? It went from 1 to 0, so this is being reduced, which means it's the cathode. And then this one must be oxidized, anode. All right, I have my little handy-dandy table here, which I actually circled this one earlier because we needed it. This is the copper, so 0.34. And the silver, we did this one a few times. It's down here. I'm actually figuring out where that one is, 0.80. By the time I teach it next semester, I'll have forgotten, but that's okay. All right, so for E cell standard, I just do cathode minus anode, so 0.80 minus 0.34. And I got 0.46. That's standard conditions. Now for non-standard conditions, I need the Nernst equation, and the Nernst equation is on your equation sheet. It's in 2 different forms. Neither of them were really the one that I usually use, so I mean, however you want to do it, but it's the E cell, and then let me make sure I got the right. Yeah, so they have the minus RT over NF, like this. Let me just write it. RT NF. I forgot to print the equation sheet. I have it on my computer, though. It also has the log log with the 0.0592, but remember, I just used this one, but I put in the number. Just use whichever one. It doesn't matter which one you use. They're all the same, but this one is the one that I'm used to. Okay, so the E cell is what I just got from my previous answer, 0.46 volts. And I need the number of electrons that will transfer, so I could write half reactions if I want to. I really need a balanced equation to get Q nailed down, but I have that, so I don't necessarily need half reactions, but I can see like the copper has to have 2 electrons to go from 0 to 2 plus. The silver, 1 plus to 0 is 1 electron, but since there's 2 of them, that's 2 electrons. So I can see that this is 2 electrons, or you can just write the half reactions and see what it is. And then natural log, and then I just like to do Q off to the side because it just seems easier. So remember, Q is just like an equilibrium product, an equilibrium constant, products on top, solids and liquids do not get included. So this is just going to be the copper on top. Silver will be on the bottom. Remember that the 2 means it gets squared. All right, so they told me 5.75 times 10 to the minus 4 and 6.31 times 10 to the minus 3 squared. And so for Q, I got 14.4. So then I can do the natural log of that times 0.0257 divided by 2. And that's this whole part then, 0.0343. And then I can do 0.46 minus that. So I got 0.43. All right, and last but not least, we have a KSP problem. So for KSP, remember we want to start from a balanced equation. I guess I could write that down there because, well, I'll need it in a second, but just kind of keep that in mind. So it's separated into calcium and 2 fluorines. So to figure out the molar solubility, I'll set up an ice table. So I should have just written this down here. Remember, this is a solid, but these are aqueous. So we don't know how much we have of the solid, but we have 0 and 0, minus x plus 2x for the 2, and so x, 2x. KSP would be calcium and fluorine squared. That's the products. The reactants go on the bottom, but since that's a solid, it doesn't get included. 3.9 times 10 to the minus 11th equals x times 2x squared, which is 4x cubed. So I can solve for x. I just like to raise it to the 1/3 power, but however you want to do it, you should get the same answer as me, hopefully. 2.1 times 10 to the minus 4. Remember, your x is how much dissolved in molarity, because ice tables are always in molarity. So this is the molar solubility in moles per liter. To convert it to solubility grams per liter, I just need the molar mass. So this is calcium, periodic table back here, 40.08, and fluorine, 2 of them, so 78.08 grams per mole. And so I get 0.016 grams per liter for the solubility in grams per liter. And finally, we have the molar solubility if it's in a sodium fluoride solution. Remember, this is a strong electrolyte. I do have the list of solubility rules on my equation sheet, and so this is going to totally separate no matter what. This is just going to do what it does, and it's going to make 0.1 molar of this and 0.1 molar of this. So then I just set up my ice table just like I did up here when I try to figure out what's going to happen to the calcium fluorine. That's all I care about, or the calcium fluoride. Except instead of 0 and 0, I have 0 and 0.1. All right, now we have minus x plus 2x. And then I have x and 0.1 plus 2x. Then I use my same KSP equation up here, 3.9 times 10 to the minus 11th for KSP. Calcium is x. Fluorine is 0.1 plus 2x squared. Assume x is small. And then I get 3.9 times 10 to the minus 11th times x times, now I just have the 0.1 squared. So I'll divide. .9 times 10 to the minus 9th equals x. Again, x is the molar solubility, so that is my answer. All right, that's it. Good luck. Let me know if you have any questions.